Hello, method students. In this last chapter of the semester, you will learn how to analyze and display the correlation between two categorical variables. You already know how to make clustered bar graphs, which is one way to do it. You will learn today how to read two-way tables and how to use the chi-square statistic. A two-way table is a good way to display data when you want to illustrate the correlation between two categorical variables. So one variable is shown in the rows and the other one is shown in the columns of the two-way table. Every two-way table can be turned into a clustered bar graph as well. This two-way table is an example. It shows two categorical variables that describe a population of 338 subjects. The two categorical variables are the political affiliation, you see it on the left, in the column on the left, and the favorite ice cream flavor that you see on top of the table. And the 338 subjects studied here are the 338 MPs of Canada, members of the Parliament and the House of Commons. These are based on the results of the last Canadian elections in 2019. Here in this two-way table, the political affiliation of subjects is shown in rows. What you see highlighted in blue here is a row. For example, the first row shows liberals. 121 of them prefer chocolate ice cream, 26 prefer vanilla, 10 prefer orange, for a total of 157 Liberal MPs in the House of Commons. Columns here represent ice cream flavors. So, for example, what you see here highlighted in blue is the column for chocolate. So if you read the table, 121 chocolate lovers are liberals, 65 are conservative, 11 are Bloc Québécois, 7 New Democrat, and 3 other, for a total of 207 MPs who have chocolate as their favorite ice cream flavor. And what you see here in blue is called a cell of the table. This table here has a total of 15 cells. The totals do not count as cells. So this table has 15 cells representing the correlation between the political affiliation and the favorite ice cream flavor of my 338 Canadian MPs. If I look at my table carefully, I can see something. I can see that the cell in which I'm expecting the most MPs, the highest number, is the one highlighted in pink here, is the one that makes the correlation between liberals and chocolate ice cream, because liberal is the most popular political affiliation among MPs, with a total of 157, and chocolate is the most popular ice cream flavor with a total of 207. So it would be normal to have in my table the cell with the highest number of MPs being the cell that correlates liberals and chocolate ice cream. And this is actually where I do see my highest number. And the cell in which I expect to have the lowest number of MPs is the cell for other, because this is the least popular political affiliation, and orange ice cream, because this is the least popular ice cream flavor. And in fact, it's true. I have 0 MPs with other as political affiliation and orange as favorite ice cream flavor. So this is in fact the cell in which I have the lowest number. This is where I expected to have the lowest number. So if I look carefully at all the cells of my table, are the numbers I see really the ones I would expect to see if I consider the totals of my rows and my columns? Maybe not. If I look carefully at the liberals, the row showing liberals, I see that 121 prefer chocolate ice cream and only 26 prefer vanilla ice cream. I'm expecting to see more people, more liberals, with chocolate as their favorite ice cream flavor. But really, 121, that's a very high number. It's much, much higher than 26 for vanilla. I would expect these two numbers to be closer, not showing such a big difference. Maybe there's something going on with liberals and chocolate ice cream. They seem to like chocolate a lot. If I look at the conservative MPs now, I see 65 for chocolate ice cream and 50 for vanilla, only 6 for orange. Are these numbers really what I should expect? I would expect less conservative to like vanilla ice cream. 65 and 50 are very close. And if I look at my totals for these two columns, it's 207 and 102. I would expect more chocolate and less vanilla for conservatives. So there's something going on here again with conservative MPs that seem to like vanilla ice cream a lot. If I skip to New Democrat now, these numbers are not what I'm expecting to see. Only 7 like chocolate ice cream, 5 like vanilla ice cream, and 12 like orange ice cream. I'm not supposed to see a higher number in the orange column than in the chocolate and vanilla columns, because less people like orange ice cream in my population of MPs. So there's something going on as well here. There's something going on with New Democrats and their preference for orange ice cream. There is a correlation here between voting New Democrat and liking orange ice cream. So if I look at my two-way tables carefully, I have the intuition that the numbers I see there are not the ones I would be seeing if there would be no correlation between political affiliation and ice cream preference. There's something going on. There are some correlations here. I suspect, I have the intuition that there is a correlation between voting liberal and preferring chocolate ice cream, between being conservative and liking vanilla ice cream, and between being New Democrat and having a preference for orange ice cream. And this is what I look at when I carefully look at a two-way table. I look at a possible correlation between the categorical variable shown in columns and the categorical variable shown in rows. I look at the possible difference between the numbers I see in the table, this is called observed counts, and the number I would expect to see, I would be supposed to see, if there was no correlation between my variables. These are called expected counts. So here the numbers I see in black in my two-way table are observed counts. Those I see, those I obtain when I survey the 338 MPs of Canada. This is real life numbers. But these observed counts, they are different from the expected counts, the counts I would expect if there was no correlation between their political affiliation and their ice cream preference. These expected counts, there's a way to find them. There's a way to calculate them. And this is the little formula we use to calculate the expected count for each cell of a two-way table. I take the total of the row, I multiply by the total of the column, and I divide by the total of the table. Here in my table, my expected counts are in red in each cell. So what I see here, let's take the cell in the upper left of the table, the liberals with chocolate as ice cream preference. If I want to find the expected count for that cell, I will use these numbers. I take the total of the row, 157. I multiply by the total of the column, 207, and I divide by the total of the table, 338. So 157 times 207 divided by 338 gives me 96. So my expected count for the cell liberal/chocolate is 96. And what I see here is 121. So I was right in my intuition. There is a correlation between being liberal and having a preference for chocolate ice cream. The observed count here is much higher than the expected count. Same thing for vanilla and conservatives. The observed count is 50 and the expected count is 37. Same thing for New Democrats. My observed count is 12 and my expected count is only 2. So the observed counts here in these three cells are very different from the expected counts. They're much higher. So there would be a correlation between how you vote, your political affiliation, and your ice cream preference. So I have the feeling that there is a correlation between these two categorical variables, your political affiliation and your ice cream flavor. I feel there is a correlation. I have the intuition. But in social science, as in science in general, I cannot publish the results of my research based on feelings and intuitions. I need science to support it. I need statistical tests to support these intuitions. And this is what the chi-square test is about. It's one of the statistical tests that will put numbers on these correlations between two categorical variables. To provide an example of how the chi-square test works, I use this example that you have seen already in the semester. This is a real-life situation based on a survey I gave to my method students last year. I asked them two questions. First, what's your gender? And second, which of these movies would you like to see first? These are movies from last year: Aladdin, Avengers, and Joker. And this clustered bar graph, shows the correlation, shows what people have answered in my class. In green, you see females, and in blue, you see males. So already here, by looking at this clustered bar graph, you see there's a correlation between being female and having Aladdin as first choice of movie, whereas Joker and Avengers seem to be preferred by males. So I have the intuition that there's a correlation between your choice of movie and your gender here. How statistically significant is that correlation? This is what the chi-square test will tell me, because it measures the statistical significance of a correlation. It measures the strength of a correlation between two categorical variables. This two-way table shows the same data as you have seen in the clustered bar graph in the previous slide. It shows 6 cells. It shows gender in rows and choice of movie in columns. And I have the intuition here by looking at this table that the observed counts, those I see here, are quite different from the expected counts. I would see if there was no correlation between gender and choice of movie. I produced this table with SPSS, which is a statistical software. But any statistical software, by producing a two-way table, is able to give you the chi-square statistic. And here, for this two-way table, my chi-square statistic is 7.6. There's a formula to calculate the chi-square statistic. You do not have to learn this formula. It's not in the program, so I will not test you on that. It's not in any test or any evaluation or any homework. But for those who are curious, the formula is the following. For each cell of my table, I have to take the observed count minus the expected count, I square it, and I divide by the expected count. Then the number I obtain for each cell, I sum them up, and the great total I obtain is the chi-square statistic for my table. So as you can see, the largest is my table, the more cells it has, the bigger is my chi-square statistic. So for the preceding table, the chi-square statistic given by my software is 7.6. So what? What does 7.6 mean? Is it a big number? Is it a small number? Is this number statistically significant or not? I don't know. I have to take into account another number in order to know it. And this other number is what I call the degrees of freedom of my table. So to calculate that degree of freedom, I have to use the following formula, which is very easy. Number of rows minus 1 multiplied by number of columns minus 1. So here in my table, I have 2 rows and 3 columns. So 2 minus 1 multiplied by 3 minus 1. 1 times 2 is 2. So my table has 2 degrees of freedom. Now I have the 2 numbers I need to be able to determine how statistically significant is my correlation between my 2 categorical variables. I have my chi-square statistic, which is 7.6, and I have the degrees of freedom of my table, which is 2. So I have the 2 required numbers. I can find the significance level, which tells me the statistical significance of my correlation, and this is expressed by the letter alpha, in the Greek letter alpha. In order to find the significance level with my 2 numbers, I have to use this table. This table is produced by statisticians. It does not vary. In any textbook or website that you will use, it will be the same table. So first, I have to look at the degrees of freedom. Here, I remember my table had 2 degrees of freedom, so I use the row of number 2. It is highlighted here in pink. And then I try to locate my chi-square statistic on that row. My exact chi-square statistic is never really on the table. I have to do my best to locate it somewhere. So here my chi-square statistic is 7.6. I see that it stands between 5.99 and 9.21. It will be there where the red arrow points. Which of these numbers do I use? If my chi-square statistic is in between, I use the smallest number to play safe. I use 5.99. Once I obtain this number, the one with the red circle, I look at the corresponding significance level alpha on top in broad characters, and this significance level is 0.05. It is in the red rectangle there. This is the number I want. This is why I wanted to have the chi-square statistic for my table. This is why I wanted to know the degrees of freedom for my table. I wanted to find out, with the help of that table, the significance level alpha. This is the key number to determine the statistical significance of my correlation. It is, in this case here, 0.05. So what does 0.05 means? It means 5%. And here it will sound a little bit paradoxical, but the smaller is alpha, The smaller is my significance level, the stronger is my correlation. Okay, so 5% here, alpha of 5% means only in 5% of the cases such a correlation between two categorical variables would be due to coincidence. So chances are here my correlation between gender and choice of movie is not coincidental, because in 95% of the cases it would be a real correlation. So most likely there is a real correlation between your gender and your choice of movie, because only in 5% of the cases this correlation would be coincidental. So most likely it is not. It is a real correlation. It is statistically significant.